Good morning students. In the previous class we have done it an electric field due to a dipole on an axial line. Today we will be doing electric field on an equatorial line of an electric dipole. So, first of all we should know what is equatorial line means. It is nothing but if you draw a perpendicular bisector on a dipole, then any point on that perpendicular bisector we can consider and we can find out. So, this is our dipole. This is a perpendicular bisector I have drawn. So, this is called as an equatorial line. So, let us assume any point on the equatorial line, say this is P, then just join PA and PB. So, in the same way how we have done for the axial line, separately we will find out the electric field at point A, that is due to a minus q, electric field at point P due to this minus q charge which is placed at A. Similarly, we will find out an electric field at point P due to an charge plus q which is placed at B. So, let us start. Electric field at P due to minus q charge. So, it will be equal to K q by the distance between the point and the charge, that is A P square. This total length of a dipole we have assumed has 2A. So, this will be A, this will be A. Now, what is AP here? And this distance from the center, this distance is R. So, if I just use a Pythagoras theorem, we have AP is equal to nothing, we will get K Q A square plus R square, and this is E of say minus Q. And what will be the direction? Now, let us see the direction. As I said yesterday, if you have a minus Q charge, the direction of the electric field will be towards the charge. So, here if I want to show, because I am going to find the electric field at point P, so what will be the direction? It will be like this. So, I can just write E of say minus Q. Now, similarly for the electric field at again at point B due to a plus Q charge will be E of plus Q is equal to K Q upon BP square. And here once again the BP will be same as AP because it is forming an isosceles triangle. So, this will be equal to KQ A square plus R square. And what will be the direction here? If it is plus Q, it will be moving away. So, if I want to show here the electric field due to plus Q charge, it will be like this, E of say plus Q. Here also we should write the direction. I can just take a mod, it is a vector quantity. So, this will be along PA, and here it is along, it is moving in this way. So, it is BP. Now, if you see the electric field at point P due to minus Q and plus Q charge, the values are same, only the direction is different. So, let us just find the resultant of the two. For this we can use a resolution of the component if they are in the vector form. Again let us recall what it is. Suppose you have a vector quantity say P here. So, you can resolve it into two components, and suppose if this is theta, this will be a P cos theta and P sin theta. The same way now I can, what is my vector quantity here? E of plus Q and E of minus Q. So, let us resolve this into two. So, for that let us assume this is say theta. So, if this is theta, then this again will be theta. So, how I can resolve this E of minus Q? Along this direction it will be E of minus Q cos theta, and along this direction it will be E of minus Q sin theta. Similarly, if this is theta, again you will see that this again will be a theta. Why? Because again you can just use a simple theorem for the triangle. The exterior angle is equal to sum of the opposite interior angles. This is again a theta because of the isosceles triangle. So, this again will be a theta. So, again you just resolve what it will be, E of plus q cos theta, and here E of minus q sin theta. Now, if you see E of minus q, sorry, it will be plus E of plus q sin theta and E of minus q sin theta, they are equal and opposite. So, they will cancel. So, the net electric field due to a dipole will be E minus q cos theta, E plus q cos theta. So, let us write the net electric field. This will be equal to E of minus q cos theta plus E of plus q cos theta. Since these values are same, their magnitude are same, so I can write 2 of E of minus q cos theta. Now, let us put the value of this E of minus q or any, both are same. Now, just see what is cos theta again. If you just see a right angle triangle, the cos theta will be equal to A upon r square plus A square. So, it will be square root, of course. So, what is the net electric field? Will be equal to 2 K, I can write this A here, Q upon A square plus R square raised to 3 by 2. Let us see what will the direction. The net direction is in this way. I can write along minus x direction or along minus x axis. Now, again we want to write in terms of a dipole moment. So, I can write this 2aq has a p. So, it will be equal to p, I can write k here, it will be a square plus r square raised to 3 by 2. So, this is my final result. I should write in this way. Now, again let us see how we have done it for the axial line. If the dipole, the size of the dipole is very small, then I can assume this A very small as compared to R. In other words, I can write R is quite large as compared to A. So, in that case I can neglect this A value. So, what is my final result? You will get E dipole is small. So, E will be equal to, so we will be going to neglect this. So, it will be equal to K P R cube. So, this is all about the electric field due to a dipole on an equatorial line. Now, let us see one more important subtopic. When a dipole is placed in an electric field, what happens to the dipole? So, let us see that. So, let us see what happens when a dipole is placed in an electric field. So, suppose we will just make a dipole in this way. This is my say point A, point B. Point A is, at point A it is plus q charge, and at point, suppose this is being placed in an electric field, and suppose this is making an angle theta. So, just see what is the force which is acting at point A and B. The force acting at point A will be Q of E. How it has come? Because in the last class we have seen that E is equal to nothing but force per unit charge. So, F will be equal to Q E. And what will be the direction? It will be opposite to the direction of the electric field. And at B, again it will be Q into E, it will be along the direction of the electric field. So, here you are observing that these two forces, they are equal and opposite and their line of action is different. So, what will happen? They will constitute a couple. So, there will be a torque, that is there will be a rotatory motion. I hope you understand what do you mean by a line of action. I will just give you one example. Suppose you have two forces are acting in this way and they are equal, say 5 Newton and 5 Newton. If you apply it, anything will happen to this body. You can just take this body as this, nothing will happen. Why? Because their line of action is same. But here you are seeing that this is moving in this way and this is moving in this way. So, their line of actions are not same. So, they will constitute a couple and hence there will be a torque. So, let us now calculate the torque. So, the torque will be equal to what is that? It is equal to nothing but either of the force into the perpendicular distance. What is the perpendicular distance? Suppose this is my C point. So, the perpendicular distance is BC. I will not write this into sign because then you get confused with the cross product in the beginning. So, I will just write in the bracket, that is a perpendicular distance BC, and this is equal to, now what is the value of force? It is QE, and what is BC in terms of a length of a dipole? It is 2a sin theta. Again this can be written as Q, just rearrange it. This is a vector quantity, this is a vector quantity which we represent as a tau. So, this is what? This is dipole moment. So, P E sin theta, and this is what P E sin theta is what? It is a cross product, like you must have seen it. C is a vector, and if A is also a vector, then A cross B is equal to nothing but AB sin theta. So, we can write in this way, tau is equal to P cross E, both are a vector quantity. So, this is a very important expression which we will be using to solve the numericals. Now, let us see some of the condition when the torque will be maximum, when it will be in the stable state, when it will be in the unstable state. So, just see the conditions. When first, when it will be maximum? When theta is 90 degree. That is a dipole and the electric field are perpendicular to each other. We will get tau is equal to P E. This is a maximum. Second, when theta is equal to 0, what will happen? Sin 0 is what? 0. So, tau will be 0. This is called as a most stable state. And then third one, if theta is equal to 180 degree, just it is reverse the direction. The direction of the dipole and the electric field are just opposite. So, it is the most unstable state. What is the value of tau we will get? It will be minus of PE. So, it will be unstable state. So, now the next topic is Gauss theorem. So, before going to what is Gauss theorem, we will see two important terms related to the Gauss theorem, that is an area vector and the electric flux. So, let us see what is an area vector means. Usually if I just assume only an area, it is a scalar quantity, but in many of the situations we have to take it area as a vector quantity. Let us see what it is. Suppose you have a surface like this. So, the area vector, it always acts perpendicular to the surface ds. Suppose you have, suppose if I just assume this, you are just taking, this has my surface, So, what will be the direction of the area vector? It will be just perpendicular to it, that is a normal to the surface. So, how I can write? ds, it is a say vector quantity, it is equal to, suppose this whole area is say a ds. So, ds n cap, that is a direction of perpendicular direction, I am just assuming has n cap, a unit vector. So, I can just represent a area vector has ds n cap, where n cap is a unit vector which acts normal to the surface of the area. Now, let us see what is electric flux. Suppose we just assume any surface, say, and suppose you just take a small surface area in this, you will see that the electric flux is the lines of force which crosses the surface normally. So, your electric flux, the direction of the electric, suppose the direction in this, I am just keeping the whole object in an electric field, and the direction of the electric field is say in this way, okay, and I am taking this part, I want to find out at this particular part what is the electric flux. So, it is nothing but a lines of force which crosses normally. So, I have to assume in this particular direction, and just if you see correlate with the area vector, this is the area which I am assuming it. So, the direction of the area vector is this. So, all those lines of force which is crossing this area normally. So, we have to take a component. So, just if I assume like this is this and this is making an angle of theta. So, I can just write down here theta. So, it is a component of E which is acting in this direction. So, all those lines of force which is crossing this particular area normally will be the electric flux. So, we are seeing that the electric field is depends upon, of course, and electric flux depends upon the electric field, and that too a component along the direction of the area vector. So, how I can write the expression for it? It is represented by phi, this is equal to E cos theta ds or E ds